Hello guys, good morning. Um, we will now be discussing transformation law uh, to deal with the stress analysis later. We need to find a procedure or a method on how to deal with the rotation transformation, especially when dealing with three-dimensional cases. So in general, if we consider two sets of coordinate system or coordinate axis, we normally designate the axis transformed from an unprimed set of coordinate system to a primed set of coordinate system. That is, if you have here in a two-dimensional format, uh, a coordinate system defined by the x and y axis, so we may therefore make a transformation from the original xy axis to another set of coordinate axes, say x prime, y prime, okay? Such that when we reference a tensor of any order to the new set of prime axes, we can readily use a transformation procedure and come up automatically with the description of the tensor or vector to the prime coordinate system. So in a two-dimensional scenario, the transformation may not be very difficult because we only need to determine the angle upon which your original unprimed axis is changed to a different location by, let's say, theta, such that eventually the other axis may be referred to the same, okay, rotation, okay, transformation. So the computation in usual mechanics is only to get the the component or the perpendicular projection of your vector, whatever it is, to the new coordinate system. Okay, so if I want to get the component of the x prime, I just make use of a projection from the original x and projection from the original y. Okay, and such that we know that this is theta. This is simply the complementary angle, which is 90 minus theta. And doing a cosine, okay, projection of such, we can say that your new x prime is simply equivalent to the old, okay, or the unprimed x, the cosine of theta, okay, plus y, the cosine of 90 minus theta. Okay, so this transformation from the unprimed to the primed axis now constitute what you call a value or a matrix of direction cosines, in which if we again deal with a very uh, or a higher order tensor and doing it in a three-dimensional spatial transformation will be a little bit difficult. So let's find a better way of dealing with it using indicial notations and operations, so as to simplify again the procedure when we deal with some algorithms uh, to be used in programming. Okay, so the transformation from a three-dimensional spatial description, no, from an unprimed axis. So this is the old or unprimed set of coordinate system to the prime set of coordinate system is actually given by these values here, okay, which are actually the coefficient matrix, or what you call the matrix of direction cosines. So all of these values constitute a 3 by 3 matrix which defines your transformation matrix in this order, okay, where A is the matrix of direction cosine, also known as the rotation transformation matrix. So sometimes we uh, abstain using the word rotation, since transformation normally are done on the basis of rotation. Although of course translational transformation may also be existent in the procedure in structural mechanics, but this is translational transformation are easier to define, uh, much less difficult than rotation transformation. Okay, so if we now define A1, A11, A12, A13, etc. on the basis of direction cosine, we can simply substitute the value of A11, etc. by the cosine of the angle, okay, wherein the first subscript is always referred to the original set of coordinate system, and the second subscript refers to the new set of coordinate system. Okay, so to demonstrate to you the use of such transformation in stress analysis, so let's have this example wherein we first try to derive the transformation equation. We need to convert a stress tensor described in the original set of axes to the new set of coordinate axes. So we know that from the stress vector formula, no, or the traction vector formula, which is actually also known as the Cauchy stress equation or formula, we note that sigma I is simply equivalent to nj sigma ji. So this sigma ji or sigma ij uh, won't mean any danger, would not mean any danger, no? Even though we make use of a different uh, position when it comes to the subscript ij. We do not worry about it any longer, because we have proven that sigma ij and sigma ji are just the same, okay, because they are symmetric. But of course, if you can do it much more mathematically correct, just like how it was introduced in the references, so better. So we now define a transformation based on the above, okay, above uh, formula. So where the prime axis is converted, or sorry, the unprimed axis is converted to a prime axis by a transformation matrix Aij. And this is also true when you want to convert a vector, okay? A vector which can be thought of as a unit direction vector converted from the unprimed to the primed axis by a transformation matrix AIR. Okay? So knowing the fact that these two here are contributory to the formulation of the transformation equation, then we say that if I now substitute, okay, the value of the stress vector nj sigma ji to this prime, okay, prime axis by simply putting a prime symbol here, so it just becomes an n prime j dot sigma prime ji. Okay, so I just place a symbol to refer to the new set of coordinate axis, and this is equivalent to AIR, and then again I just substitute the stress formula or the stress vector formula on the sigma r without any prime. So this is now an ns sigma sr. Okay, so I have to be consistent for to be able to capture the correct formulation. Okay, so ns can also be defined in terms of the prime axis. So we just reverse this equation. Now if you can come up with a prime axis, let's say y I prime is equivalent to a ij yj. We can also come up with a yj, okay, equivalent to AJI yi prime. Okay, so this is true with this particular notation. So this is now ns is simply ASJ n prime j. So I'm converting now a prime axis to an unprimed description of my normal vector because I want to substitute this here. Okay, and if I substitute here, I can have the same subscript n prime j with that of the left hand side n prime j, and taking note that I can simply cancel, okay, cancel out the n prime j here. Okay, but take note that that my sigma sr eventually is at the far end side of the triple product. So I don't have again to worry about the subscript SR or RS since sigma SR is equal to sigma RS. Okay, so strictly speaking, it doesn't matter to me because this is again symmetric, and therefore if I can simply uh, uh, cancel n prime j here, noting that what will remain is AIR, ASJ, sigma SR. But why did I make use of an AJS here? Because the mere fact that I remove one tensor here or one vector here, since the transformation matrix, note that the transformation matrix is not, okay, is not symmetrical. or is not symmetric, unlike the stress tensor, then I have to interchange my ASJ subscript to an AJS subscript for this to be consistent. So because this is inside the parenthesis, and I want to remove that parenthesis, so I now come up with such a subscript to make my formulation, my equation, accurate later when I use it. And I will prove to you that this is very critical in terms of using it uh, as a transformation formula. But simply enough, we can now convert, okay, the initial equation. So this is now an initial formulation to a matrix multiplication, or simply a dot product operation, by taking note that A and A here are simply the transformation matrix, but we have to place a transpose there, okay, simply to uh, allow us not to have a different, okay, uh, result, because again, as I have said, your transformation matrix is not symmetric. Okay, so take a look at the position whenever you come up with such formula. You may choose from using this transformation formula and this matrix multiplication formula to your advantage. Okay, where sigma prime ji is the stress tensor described at the prime axis, and sigma sr is the stress tensor described at the unprime axis. Okay, so we are now going to test now the validity of such transformation equations by way of solving this problem here, wherein the stress components of the tensor, or elements of the tensor, are given in terms of this matrix, are referred to a set of y-axis, and we are asked to find the components referred to a set of prime y prime axis rotated 30 degrees counterclockwise about the y3 axis. Okay, so I have here a drawing, a figure on what is the original axis. So this is your original unprimed set of axes, and the new axis, which are the prime axis, are these which were drawn uh, uh, by this black color here. So take note that the third axis y prime 3 is not was not moved, okay, because the axis of rotation of 30 degrees was based on a counterclockwise direction about the y3 axis. Okay, so it's just like saying that this rotated, okay, here at 30 degrees, and since these are orthogonal, then take note that our rotation is actually about the y3 axis. So this is now again at 30 degrees. So these are now the new sets of your y1 prime, y2 prime, and of course you have also a y3 prime here, which has not moved because the axis of rotation was chosen to be exactly at the y3 axis. Okay, so how do you now reference your angles? No, so take note that the set of the unprimed and the primed axis, as shown above, uses a reckoning or a reference such that the angle in between them are based or reckoned from the unprimed axis to the primed axis. So if you are going to take note of your subscript 11, A11 or theta 11, you are now referring to the angle coming from the red axis y1 to the black axis y1 prime. Okay, so that's theta 11. Okay, while theta 12 is simply coming from this red y1 to the black y2 prime. And theta 13 is coming from, again, from the red y1 to the black y3 prime. Okay, so it's reckoned um, always from here to here. Okay, from here to here. Now, the choice of having a cosine matrix, or the matrix of direction cosine, was actually made to note that the cosine of the angle which is more than uh, pi, or 180 degrees, will actually give you uh, the negative, okay, the negative of the other. So the cosine of 0 degrees is actually 1, but the cosine of 180 degrees will give you a negative 1, no? Because it will refer to the other side of the axis. Okay, so that is the reason why they choose the cosine direction rather than having a mixture of, say, cosine and sine, so as not to give us any confusion on how to set your angle reckoned from the base axis y1 to the new axis y1 prime, y2 prime, and y3 prime. So all in all, you have actually 3 times 3, 9. Okay, 9 angles to reckon from to complete your angles. Okay, theta 1, 1, theta 1, 2, theta 1, 3, etc. And these are all given here as theta ij is equivalent to this angle in degrees. Okay, so this is in degrees, and this is in radians. So just converted it to radians, okay, by simply multiplying it by pi all over 180. So you just multiply this by pi over 180, and then you can get this here. So taking note that the MathCAD tool or the calculator I will be using later will be using the radians as their basis for the unit of angles. Okay, so to determine now the matrix of direction cosine, we simply take the cosine of all these individual angles to come up with the values here here in this particular matrix. Okay, so this A here constitute these values uh, based on the cosine of the angles obtained from here. Okay, so I'd like you to take a look at how the angles were obtained, and if you have questions later, you can ask me, or we can check if there are some errors on these values. Okay, and using the transformation law on rotation to find the stress tensor described by the set of the prime axis, we can now come up with this equation based, of course, on what we have derived a while ago here. Okay, so this is the sigma prime ij IR AJS sigma SR. Okay, so we can actually take a look into the consistency of such equation by verifying the index. Okay, so it's a good so always from time to time you might as well look at the consistency of your subscript here. If this is a two index, okay, a second order tensor, because you have two free index here, I must also have two free index here, okay, which is the ij here, no, because this will collapse with that, and your s will also collapse with this. So this is a two index tensor in terms of I and j. So second order, we have a consistent uh, expression here in terms of the indices. And if I iterate on R, 1, 2, 3, I just substitute the, okay, R and R are repeated, so I have the sum, no? I will now have an AI1, sigma S1 there, AI2, sigma S2 here, and AI3, sigma S3. And I iterate on S1, 2, 3, I will come up with an AI1, AJ1, A11, okay? Because this is all 1, etc. Okay? So the first parenthesis here refers to the first term here. Second parenthesis refers here, and the third uh, expressions on this, the third parenthesis refers to this here. Okay? So all in all, I have now my how many components. So I have a vectorial, okay, a component here because my I and j are not yet substituted. Okay, so 3 times 3 there, I have 9 components which actually constitute 9 elements of the stress tensor. So second order 3 by 3 is a 9 element uh, tensor. And to find the value of the stress at row and I column, row I and column J, of course I need a calculator to do it fast, so I use the MathCAD array operation. So I just define my sigma here on the basis of my array. Okay, so I just copied this I comma 1 j comma 1 because in MathCAD they use array operation in terms of a comma, no? Okay, so this all the i's and the j's will be computed on the basis of I equals 1 and j equals 1. So if I have a sigma here, this is actually my sigma 1, 1, okay, equal to 0.018. Okay, so the good thing about MathCAD is only change the I and the j values, 1, 2. So this is now a sigma 1, 2, and then I get this one here. But look, if you are doing it using a simple calculator, it would really be very, very tedious and tiresome to do this. Okay, so here I just change I equals 1, j equals 3 to get a sigma 1, 3, and I get this one here. Okay, so I'll do it again and again until I finish all and put it in a matrix form. So my final answer, so this is now my transform stress tensor, okay, based on the problem. So these are now my new stresses based on the orientation on the y prime axis. Note that the expansion process is too heavy, and if you proceed with manual iteration, uh, it will be much more heavier, no? So we may opt to use the matrix multiplication instead, and this is only a one row or one time operation. So I just plug in an a dot sigma dot a transpose. I get automatically this one. You may check it using MathCAD, no? Want you to do it and compare the result. So these are all the same with that of the initial process, okay, the iteration process. Okay, so note about the operations we have done, and take a good look on how the properties of the rotation transformation matrix can be checked. No? So it's a good thing to note that the product of a transformation matrix and its transpose is, what's this? This is a delta ij. Okay? Okay? So when you dot an a matrix with that of a, this is actually an A I say S dot to AJR. Sorry, I'm using a different. Okay, so this is ASJ. Okay, ASJ will result to a delta IJ. So SNS will collapse. So this will be a delta IJ. And vice versa. So we can say that A S J multiplied to an A I S will also be a delta Ji. Okay, but delta Ji and delta Ij are just the same. And take note also the inverse. The inverse of A, okay, so this is a matrix inverse, is equivalent to its transpose. Okay, so the matrix inverse is equivalent to the transpose of the matrix. We're always referring to the rotation transformation matrix. This is not true with other matrices. And the determinant of a transformation matrix is equivalent to 1. So this is a determinant of A is equal to 1. Okay? So these are 4 properties you may think of as very useful, no? Very important, no? In dealing with transformation procedures. Note that the first operation proves that the product of the rotation transformation matrix and its transpose is an identity matrix. The third operation proves that the inverse of the rotation transformation matrix is equivalent to its transpose, and the fourth operation proves that the determinant of a rotation transformation matrix is equal to 1. So hope you find a good understanding now of how transformation law is done using tensor mechanics, and we will be proceeding with some other uh, principles that will help you uh, advance to the stress analysis solutions we will deal on the next lecture. Thank you very much for listening. I'll see you on the next video.